Someone please start recording. This is the presentation of Task C for Team 13, Technologists. As required of us for this project, to identify a broadly defined civil engineering problem and then solve it using numerical methods. Me and my team members, the technologists, have identified this following problem: South Africa's ailing water infrastructure issues and water shortages. The South African National Minister of Water and Sanitation recently hired 24 Cuban engineers to come and help with South Africa's ailing water infrastructure and thus water shortages across the country. Team 13, the technologists, chose to adopt this problem for this project and seek to find an amicable solution using numerical methods. South Africa has serious water-related problems that prevent people from accessing clean and drinkable water. There are a variety of issues that are as a result of this, namely the lack of sustainable water resources such as dams and rivers, the lack of and ailing water infrastructure such as water networks and water reservoirs, the lack of water treatment plants, and the lack of repair and replacement of existing water infrastructure. There are various parts in South Africa that have been struck with crippling droughts and as a result of this problem. For some, it has been years. The Greater Giyani Local Municipality is one such place. As the Technologists Team 13, we have decided to adopt this aforementioned area as our case study. In this presentation and in our reports, we break down this problem carefully and analyze and assess it and solve it using numerical methods, and then give concise conclusions and recommendations. I'll hand over to my colleague, Mr. Tlangelani Malulek.
Good day, everyone. As my colleague Vuyo Pandle was saying, during our rotation within the different directorates of the Department of Water and Sanitation under the Directorate Hydrology for full exposure in the civil engineering field as part of our numerical methods project research, we came across the use of stage measurement, water level, to determine whether the amount of water is sufficient enough or not. Therefore, our problem statement with regard to the Greater Giyani is to determine whether the amount of water that is currently supplied is sufficient to supply the whole Greater Giyani municipality, and to verify if the water that is supplied now will be sufficient also in the future, of which is from now up until 2030. I will hand over to Christine to elaborate more in terms of data collection.
Good evening, team. So this is, I'm going to speak about data collection. As my colleagues just said, our aim here was to find the demand of the Greater Giyani municipality. So the information that we got was from the Greater Giyani Local Municipality. We used information from public documents that were published by the local municipality. And those information that we got was they were verified by means of emails via talking with the people in charge at the local municipality in Greater Giyani. So this is the type of data that we collected. We collected data about population. We got the population of this March in 2016, and then population growth. We got the number of households, and then the average household size in South Africa, which was about 3.3 people per house. But then in the calculations, we assumed to be a certain amount, which my colleague is going to present. And then after that, we found data about education facilities, healthcare facilities, agricultural facilities, and other facilities like community halls, recreational parks, and offices. So all of these data helped us to find the average demand in the Greater Giyani Local Municipality. And I'm going to hand over to my colleague Daniel, who's going to present the manual calculations. Thank you.
Yeah, good day. Good day, everyone. In order to calculate, to estimate the water demand of the Greater Giyani Municipality, we need to determine the future populations. The formula below was used in this project to estimate the future population. FP equal to PP times 1 plus R to the power of N, where N is the change in years, PP is the present populations, and R is the growth rate. The water demand can then be calculated as per the guideline for human settlement planning and design. The second slide, we can appraise the results of the water demand. The municipality provides about 56 megaliters per day, and the demand as per 2021 were found to be 82.28 megaliters per day, which is greater than the current demand, and there is a shortage of about 29 megaliters. And then thus it has been proved that the water demand shortage is huge and can be regarded and measure to mitigate this can be regarded now by the government. Yes. I think that's all for the presentations. So the populations results were found from 2016 to 2030 in respect with the average daily demand, and these results can help to get the area populations, the area that need to be recapitulated. I will hand over to my colleagues who will present the next task.
Chair, I think our colleague Technologists is trying to connect to speak, but we can't hear him. I don't know, what should we do? Should we maybe try another person, and then when he's fixed his audio problem, then we can come back?
Yes, Christine, you can hand over to another one. As soon as it's done, he will just give us a shout that we can continue with him.
I'm going to hand over to Sifiso so that he can present his part.
Good evening, team. I'm going to be presenting with explaining or a presentation and overview on Octave. So Octave, it's an online. Can you move to the second slide? So Octave is a software featuring of a high-level programming language like Java, C++, C, Ruby, Python, primarily intended for numerical method computations. So Octave is used in solving linear and non-linear numerical problems. So Octave is compatible with MATLAB, which means that you can run a code on Octave, and also you can run the very same code on MATLAB without changing the code. So Octave comes in, if you install it on your desktop, you'll get two icons. So the first one is a GUI, which is graphic user interface. In your graphic user interface, codes can be coded in the editor. Then you run, the output is shown on the command tab. So it means when you run your code on your GUI, you can edit the code on the editor and then run it on your command. But now with the CLI command line interface, the code is not stored, so you're running the code directly. Okay. And then we as team as task C, team 13, so we did a drawing. So we did a graphical representation of the population design flow, of which you have your data input where it's F, and then you've got P, which is your population. So when we did our code, you had to input, as you can see on the code, it has data input. That's where you input the data, and then you also have an output. Your output is where you're having your graph, right? And then the next two slides, it's an example of how the Simpsons rule looks when it's coded, with the input and the output. And then the last one shows the trapezoidal rule, which also has an input and an output, and then all the comments are written in green. So if you want to run something that you don't want to be part of the code, you put a hash in front so that the code doesn't run through that. Then you can comment on that. Thank you. I will hand over to my colleague Palisa.
Good evening, everyone. I'm presenting on Simpson's rule. For this project, we have used this rule to calculate the area that needs to be reticulated in the proposed study. And based on our calculations, we have found that about 10,000 hectares of land needs water supply. I'm going to hand over to Mthokozisi to share with us about trapezoidal rule.
Good evening, Group 13. Here we'll talk about the trapezoidal rule. The trapezoidal rule approximates area under the curve. What we do, we go and collect data from the rivers, and then we draw graphs. After drawing those graphs, and then we then estimate and approximate area. So that will help us understand the discharge of the volume of water we can get on the river. So how does the trapezoidal rule work? It's just area is just calculating area. Just the width divided by 2, and the simple formula. So advantage about the trapezoid is just a simple formula, and then the advantage about the surface is not accurate. I will then hand over to the next caller.
Thank you, Mr. Kozisi. I will be talking about the results obtained and the analysis of previous mentioned topics for the Greater Giyani Municipality. In 14 years from today, in 2030, with the current infrastructures, Greater Giyani receives about 56 megaliters a day of water, while they need 74.43 megaliters of water per day. That equals a deficit of 22 megaliters per day. This shows that the Greater Giyani Municipality is not supplying enough water to its people because the demand is much higher than the supply. From the relationship graph between daily design flow and population, it can be seen that as the years go by, the demand increases and with an increase in the population. The value of the area under the curve obtained during the trapezoidal and Simpson's rule indicates the amount of water consumed over 14 years, ranging from the period 2016 till 2030, and is a value that future water engineers must look at when designing the water infrastructure for the future in the Greater Giyani Municipality. The time series of stream flow and drought threshold levels from the figure on my left lower corner clearly shows that the period between 2016 to 21, the water received was above 70 to 90% of median flow in the Greater Giyani Municipality. But there is still a major shortage of water because the area receives too little rainfall. The flow duration curve clearly shows the reliability of the flows is very low, and the drought or droughts in the future is very much possible for the Greater Giyani Municipality. Thank you. I now hand over to my colleague Ernest.
Thank you very much. Thank you very much. In conclusion, to our task C has proven beyond reasonable doubt that there is a greater shortage of water in the Giyani area. The river that is the source of the water in the area is not reliable for it to supply the Greater Giyani with the water. It has also proven that as we continue to increase, as the population continues to increase, the shortage of water continues to increase at the same time. How do we address a problem? How will the government address this problem? How will the society address this problem? In short, there should be an increase in the source of water, which means the government has to look around and see if they can construct more dams or they can drill more boreholes so that the source of water can be increased. Treatment plants need to be built so that the water within the area whether it's from the boreholes or from the dam, has to be purified. Thirdly, from task C, as team 13, we have noted that numerical method can be used in solving different engineering problems. Numerical integration is good in the calculation of the areas that are being affected by water shortages, and that needs to be reticulation. This has been spoken, the members that have been speaking during this presentation. The area that needs to be covered in the Greater Giyani area, that needs reticulation, right? And therefore, we recommend that we continue to use the numerical method systems to the complex engineering problem. We thank you for participating in this presentation. Thank you all.
Thank you, Chair.
Okay. So I hope our recording will end here so that it does not become too big for uploading.
Thank you, sir.